Mendelian school viewed genetics as discrete Mendelian inheritance, and evolution as a discrete process with discontinuous jumps. Like, how can it be this continuous thing without all these little jumps? And these were at war with each other. This driven by looking at the underlying mechanism, genetics and inheritance. This one looking by the observable things that we can measure. And so they're like, hey, they don't match. And so there was a decline in the belief in Darwinism during the early 1900s, which ended, by and large, with the work of R.A. Fisher and his couple other people, Sewell Wright. There's one or two other authors, but Fisher was one of the big ones. And he came up with the fundamental theorem of natural selection. And so this fundamental theorem of natural selection says the rate at which the mean fitness of a population increases is proportional to the variance, which is standard deviation squared, of the genetics in the population. So if you think about it this way, we had three bug populations. But if instead of bugs that reproduce at 3%, 4%, 5%, suppose we had bugs that would also produce at like 2%, 6%, 7%, and we had a big variation of reproduction. Then we'd have more variety to optimize over, and so our fitness would be maximized more quickly. Right? If we go back to this, our average fitness here is 4%, because we have the same amount of all the bugs. 2 years later, our average fitness is like 4.5%, because if you average over all these populations, I've got more quick reproducers. So Fisher's theorem says, and I've got the math here if you like math. If you have a population with lots of variants, so P sub I, so I've got lots of different genetic genomes, or populations with different genomes indexed by I, and you have one genome for each individual. But you've got lots of populations. This is how quickly each of those reproduces, and so there's your differential equation governing it. And then his theorem says the rate of change of average fitness, is equal to the genetic variance, which is a statistical measure. That's how much variety there is. So this was proven, and people debated, they still debate sort of whether his proof is right. The key thing here, which was revolutionary, right? By itself, the theorem, you guys understood it when you first saw my little bug pictures. By itself, the theorem is not a big deal. But when Fisher, he wrote a book, and he proved it in his book, the key thing here is that he connected genetics with the increase in fitness. So he connected Mendelian genetics with an increase in fitness. So he did a little more than what we're stating here. He didn't start with this. He started with basic genetics with some very simplifying assumptions and built through to get to that. Okay. So what people did when they saw this, when they first started working on it, people debated for a while whether his math was right. I read it, I went through his math is right, but it's written in a 1930s style. He doesn't use equations, he uses words for things, it makes it really hard to prove, so you have to rewrite it. But a lot of there's a couple of different published papers, different people redoing his derivation of his theorem. It's in textbooks too. So it's people debated whether it was correct, and they kind of still argue about whether it's right or not. Because he's not clear about, he doesn't define things the way we do math now, so it's not as rigorous as. But okay, so what this says, if you take Mendelian genetics, you get this increase in fitness, and if you look at it, you go, wow, that's evolution. Well, the question is this going to continue going? This is really just at one instant. It's the rate of increase at an instant. So what Fisher goes on to talk about in his book, which people state this theorem, and then they talk about how it's the driving force of evolution. What Fisher talks about is he says, mutations, there's no mutations here, mutations give you the variation. This mechanism, this machinery, turns that variation into improved fitness. And so that's the ongoing process. And Fisher said your mutations are going to be 50% beneficial and 50% deleterious or harmful. And his argument for that, his justification for said, if you're tuning a microscope and you're going to randomly turn the knob a little bit, you have a 50-50 chance of getting closer to being tuned properly or getting farther away. Or if I want to get somewhere far away, like France, I don't know, no idea which direction is the quickest way to France. Suppose it's that way. I have a 50-50 chance of pointing in a direction that's closer to France. So that's Fisher's argument. And if you don't understand genetics and you don't have what we have today to understand it, it's a very reasonable argument for why they should be 50-50. Right? If you've got somewhere to go, you get a 50-50 chance of randomly getting better or worse. Right? So it was a good justification for his death. So here's his corollary. He claims it. He doesn't prove it. I wrote a paper, which isn't published yet, but I have a proof of that. Proof of his theory in the paper. That if you make this assumption, then you get this ongoing evolution. So you get this process where you get your 50-50 mutations, and then your average fitness keeps going up. So here's a quote from one of the papers on Fisher's theory. And so his aim was to vindicate Darwinism and demonstrate its compatibility with Mendelism. Indeed, its necessity, given a Mendelian system of inheritance. So Mendelism wasn't, Mendel's laws were observable and testable. Darwinism was, as a whole, overall species, was not. So people went with Mendelism because it's testable science. So they needed to vindicate Darwinism in that era, and so that's what Fisher did. I love, it's this funny personal side. I love Fisher. I love reading his work because I'm like, I know what you're talking about, buddy. I mean, he's a good mathematician. He invented Fisher's linear discriminant analysis, which is, anyway, it's just central to engineering statistics. It's central to just about everything we do, but in computers. Okay, so this piece right here, mutations plus selection plus time equals ongoing increase in fitness. Philosophically, this is called the modern synthesis of neo-Darwinism. Philosophically, it enables the primary axiom. And I try to keep this a little separate because it's a philosophical thing that some people accept philosophically, some people reject philosophically, and people debate a lot about the evidence for it. Okay, so I just want to leave it, honestly, to be honest, we debate a lot about the evidence for it. But the thing is that this enabled that. And so up to this period, this idea had wavered, and now it's back because of what Fisher did. Okay, so questions up to there?
I am to say the same thing about random selection. I mean, that has a technical meaning in biology that is not, I take it what we're talking about here. I would also say that equation also needs heritability in it up there. Heritability is also necessary for ongoing increases in fitness.
Yep, good. That's true. This is a simplified, definitely could take the word random out there. Selection is, there's a lot that goes into selection. Yep.
Just about the wording you have, it says ongoing increase in fitness. Do these sort of take that, do you intend for people to sort of interpret that as time goes on, creatures will get better and better, just like the idea of progress?
Yes, and Fisher said that was inevitable, it was unstoppable. It was a process that was unstoppable.
As long as it's 50-50.
So, assuming 50-50. And he's correct, if you had 50-50, you would have an unstoppable process of evolution. The problem is, if you think about microscopes, if you're very close to being tuned to the best, if you've taken the time to tune your microscope to focus it properly, somebody walks up and does a random tweak, you're probably going to get less focused. Right? And so genetics are very well tuned, they're also very complicated. So here's the problem for Fisher's corollary. The vast majority of mutations are deleterious. So it's from this article here. This is standard understanding of population genetics. It's not often presented in biology classes because we like the idea of mutation, selection process. And if we all understood that most mutations are deleterious, deleterious means it hurts the